Imagine this. You're perched atop a majestic mountain, the world still asleep beneath a blanket of stars. As you wait, the eastern horizon begins to glow. A faint purple hue gives way to fiery orange and brilliant gold. The sun, a celestial artist, paints the sky with breathtaking colors. What creates this stunning spectacle? It's all thanks to light and its incredible properties. Light is more than just what our eyes see. It's a form of energy that travels in waves, much like the ripples on a pond. These waves, however, are electromagnetic, a combination of electric and magnetic fields vibrating in harmony. Understanding these waves unlocks the secrets behind light's mesmerizing behavior. But there's more to the story. Light doesn't just travel in straight lines. It can bend, scatter, and even interfere with itself, creating a world of visual wonders that we often take for granted. Let's delve into these fascinating phenomena and uncover the magic woven into every beam of light.
We often think of light traveling in straight lines. While that's true in a vacuum, like outer space, light behaves differently when it encounters matter. That's because light travels in waves, and these waves interact with the particles they encounter. Think of it like this. Imagine ocean waves approaching a shoreline dotted with rocks. The waves don't simply stop at the rocks, they bend around them, creating new patterns. Light waves behave similarly when they encounter particles in the atmosphere or pass through narrow slits. These interactions lead to fascinating phenomena like scattering, interference, diffraction, and polarization. These might sound like complex scientific terms, but they are responsible for everyday wonders like the blue sky, the shimmering colors of a soap bubble, and even the effectiveness of polarized sunglasses.
Ever wondered why the sky is blue? It's all thanks to a phenomenon called scattering. When sunlight enters the Earth's atmosphere, it collides with tiny particles of air, like nitrogen and oxygen molecules. These collisions scatter the sunlight in all directions. Here's the catch. Blue light, with its shorter wavelengths, scatters more effectively than other colors. That's why we see a predominantly blue sky. During sunrise and sunset, sunlight travels through a larger portion of the atmosphere. This longer path causes more scattering of the blue light, allowing red and orange hues with their longer wavelengths to dominate the sky. Scattering isn't just limited to the sky. It's also responsible for the milky appearance of opals, the blue color of some bird feathers, and even the red glow of stop signs at night.
Light waves, like any waves, can interfere with each other. This interference can either amplify or diminish the light, creating captivating patterns. A classic example is the double-slit experiment. Imagine shining a light source onto a screen with two narrow slits close together. You might expect to see two bright lines on the wall behind the screen, but something remarkable happens. Instead, you see a pattern of alternating bright and dark bands. These bands are a result of interference. When waves from both slits arrive at the screen in sync, their crests and troughs align, resulting in constructive interference and bright bands. Conversely, when waves arrive out of sync, their crests coincide with troughs, leading to destructive interference and dark bands. Interference patterns aren't just a laboratory curiosity. They're responsible for the iridescent colors of soap bubbles, the vibrant hues of some butterfly wings, and even the functioning of lasers.
We often think of light traveling in straight lines, but it has a knack for bending around corners. This bending of light waves as they pass through an opening or around an obstacle is called diffraction. Think of a water wave passing through a narrow opening in a barrier. The wave doesn't just continue in a straight line, it spreads out, or diffracts, behind the opening. Light waves behave similarly, though the effect is less pronounced due to their much smaller wavelengths. Diffraction is why we can hear someone talking around a corner even if we can't see them. Sound waves, with their larger wavelengths, diffract more readily than light waves. Diffraction is also crucial in optics, enabling the creation of telescopes, microscopes, and even the human eye.
Light waves are transverse waves, meaning their vibrations occur perpendicular to the direction of their travel. Imagine a wave traveling along a rope. If you shake the rope up and down, you create a transverse wave. Polarization is a phenomenon that filters these vibrations, allowing only light waves oscillating in a specific direction to pass through. Think of polarized sunglasses. They contain a special filter that blocks horizontally polarized light, effectively reducing glare from reflective surfaces like water or pavement. Polarization isn't just about sunglasses. It's used in various applications, from LCD screens and 3D glasses to scientific instruments that analyze the properties of materials.
From the vibrant hues of a sunrise to the intricate workings of our eyes, light underpins a vast array of natural phenomena and technological advancements. By understanding the fundamental properties of light, its wave nature, its ability to scatter, interfere, diffract, and polarize, we unlock a deeper appreciation for the world around us. So the next time you marvel at a rainbow, the shimmering colors of a soap bubble, or the clarity of a starry night, remember the unseen dance of light waves that makes these wonders possible. The study of light is a journey of endless fascination, illuminating not only the physical world but also the boundless potential of scientific inquiry.